Hi, everyone. Uh, Such a pleasure to be here. It's an honor to
Now it's an honor.
now, yes, now it's an honor to take part in a conversation that has given me a lot over the years, uh, and I'm really pleased to reciprocate today with this talk. And I want to start with a claim that I think is becoming more obvious every day that we exist in a state of deep entanglement with our technologies. For decades, we've understood that our thinking doesn't just happen inside our skulls. We operate within what Catherine Hales has called cognitive assemblages, dynamic networks where human cognizers and technical information processing systems interact and co-evolve. And this entanglement is no longer just a matter for philosophy. It is actually actively reshaping our planet. In the Anthropocene, some of our most critical ecosystems are now what we might call techno-ecological systems. They're dependent on a vast infrastructure of monitoring, management, and care. And during my own fieldwork in Sweden, I saw this firsthand. How do you think forest managers oversee millions of hectares of state-owned land? They're not just walking in the woods, they're at their desks using satellite data and machine learning to spot illegal logging. And they're using vast digital databases and statistical software to manage the health of the forest. And this isn't just a niche activity. The EU has just passed a law using machine learning to check for deforestation in the supply chains of coffee, soy, and rubber. So the takeaway is this: the management of our living world, the semiosphere, is now deeply dependent on these cognitive assemblages of humans and machines. And as these human machine assemblages are increasingly becoming human AI assemblages, we are compelled to engage in what the late Jesper Hoffmeyer has called a biosemiotic reframing of our technological challenges. But to understand the interplay between humans and machine learning, we first have to set aside a misleading question. The question is not whether these machines are proto-semiotic, whether they are approaching a threshold of meaning. I think Winfred Noth has argued a convincing case for why there can be no machine semiosis. However, I think we should be careful not to get trapped in a linear model. This would frame the problem as a linear continuum with some things before the threshold of meaning and some things after. Instead, we need a different starting point. So I want to propose we shift our perspective. Instead of a line, let's think in terms of a nested hierarchy. And the framework I'm proposing is one of constellational enfoldment. And the idea is this: a higher level human cognitive process functionally enfolds the automated operations of its cognitive artifacts. And we can go through some examples. Consider a sentence. The full meaning emerges at the level of a sentence, but it's completely dependent on the words, which are dependent on the letters. So the higher order enfolds and gives meaning to the lower orders. We could also use a biological analogy. A human cognitive act can subsume an automated computational process to some extent, like an organ subsumes the functions of its constituent cells. Some of an organ's higher order functions could not exist without the biochemical processes that support them. Just like certain human cognitive functions could not exist without the cognitive artifacts that support them. This principle of nested hierarchy is also a cornerstone of Terry Deacon's work, appearing both in his semiotic and dynamic theories. So in his semiotic theory, where he builds on purse, symbols are understood to be composed of indices, which are in turn built from icons. So a higher order sign type requires and organizes the lower orders. Likewise, in his theory of causality, goal-directed teleodynamic action requires and constrains an underlying morphodynamic form. This same hierarchical logic is, of course, the bedrock of Peircean semiotics, where thirdness organizes secondness, which requires firstness. Adopting this nested view allows us to see automated learning systems not as external to our minds, but as a constitutive lower order element integrated into the very fabric of our own sense making. And my argument here is not just that external cognitive artifacts exist at a lower layer in a hierarchy of levels, but that they're fully interwoven into a coherent web. But we can make this more concrete. So imagine a team of ecologists using machine learning to find whale calls in a vast ocean data set, as we heard about yesterday. So the machine does a low-level work. It churns through the data and produces coherent patterns with plant design vehicles. But it's the ecologists who perform the higher-order act of sense-making. They look at a pattern and ask, what does this signify? Is this a new mating call, sign of stress? So here the ecologist's sense-making is a broader, more complex whole that enfolds an automated process. And if we grant what's been said so far, we can see the relevance of an old inquiry of semiotics in a new light. That is the inquiry into the action of science. And what really interests me here is the causal nature of automated learning systems. Do these systems simply exhibit the familiar efficient causality that characterizes simpler computational devices? Or are we witnessing the emergence of a different kind of causality in them? To explore this question, I chose a model system. Instead of looking at a complex neural network, I chose a much simpler system, an algorithm called random forest. This model was developed in the 90s by a statistician called Leo Breiman, but its modified form persists today as the most popular algorithm for making predictions on tabular data. And I think is a perfect microcosm for examining what kind of causality is at work in machine learning systems. So let's imagine that we're training this algorithm to do a simple task, to recognize handwritten digits. Each item in our data set here is a digital photograph of a handwritten digit. But let's pause on this image, because what is it really? When a camera sensor captures the light from a handwritten digit, a physical transfer occurs. The structure of light creates a corresponding structure in the electronic signal. That signal now carries a physical trace of that original structure. But, and this is the crucial point really for my whole argument, that signal is not just a physical artifact. From a biosemiotic perspective, it's a sign. And as John Deely always insisted, signs are fundamentally relations. So that signal embodies a real relationship to the object it captured. Now, it may not be a fully formed sign. The interpretant is still only potential. It's what Peirce called a would-be. But what this means is that each physical sign vehicle going into the computer is more than just a physical sign vehicle. It's just the detectable tip of an iceberg, the visible part of a vast latent web of a relation that subsists within the signal itself. Because the sensor that captures this emitted light is very intricate, tens of thousands of discrete values are produced, and each value is what is called a pixel, and each pixel is the encoded value of the intensity of light that struck the sensor, always consisting of a value between 0 and 255. Small images like these might consist of around 10,000 pixels. So for a computer, An image is just a long list of numbers. And in terms of computer hardware, each number is a configuration of electrons within memory. And what the computer receives then, at the start of its training phase, are thousands of such images, each of them paired with a label that states which digit it represents. And the computer's goal is simple. Take this list of numbers and output the correct label. How does it do this? The algorithm starts this process by creating a split in the data set. It starts with a random pixel location, say location number 124, and it then poses a random if-then condition. Is the value in this location greater than 55? It then moves all the images where the value of pixel number 124 is greater than 55 into one memory location, and all the images where it's less into another. It then takes all the images in the first pile and it counts the labels for all the images. And then it does the same for the second pile. Then it compares the label counts for the two piles. And now it poses another if-then condition. If making that split increased the occurrence of one or more types of labels in one group, but not in the other, then it's considered a good split. And it does this again and again and again, trying every possible split on every value and every combination of possible splits. And it selects only the splits that maximize the similarity of labels within a group. Now, of course, each of these interactions are fully dyadic, driven solely by efficient causality. Each time the system makes one of these calculations, we just find a mechanical process whereby transistors are shuffling electrons through different kinds of logic gates. This is just pure secondness, brute cause and effect, not mediated by any law, habit, or rule. In any event, after it has run through its training phase, we get a sequence of if-then conditions such that when it receives a fresh image and it has no labels to go by, it can apply the sequence of if-then conditions to the list of numbers and hopefully produce the correct label. But here's the problem. A single tree that's built in this way is really quite dumb. It essentially just memorizes the training data. If you show it a new digit written by someone with a different handwriting style, it will almost always get it wrong. It fails to generalize. And Leo Bremen had an interesting solution to this problem. He said, instead of growing one perfect tree, let's grow a whole forest of imperfect ones, hundreds of them. Each tree will be trained on a random slice of the data. And so because of this, each tree learns a slightly different set of rules and makes slightly different predictions. And now, when we show the system a new unseen digit, we don't just ask one tree, we ask all of them in parallel. And now we get hundreds of different answers. And then the final crucial step, the system takes a vote. It aggregates all the predictions and chooses the most common one. And what Ryman found was interesting. This forest of mediocre individual trees, when acting together, predicts the correct digit with very high accuracy. So what have we just witnessed? What has been produced here? What has been produced is a trained model, but we can be more precise. What has been produced is a set of formal relations. This set of formal relations will reliably mediate the relation between an image and a category. In other words, the model is a rule or habit that will consistently channel the movements of the automated system towards a specific end state based on the formal properties of the Stein vehicle it receives. This rule was not prescribed by its operators, but grew out of the interactions between the elements in the system. How did this happen? Each tree was just a guess at the rule that underpinned a form-generating process. But since each of them individually failed to approximate the habit that gave rise to the patterns found in the data, we aggregated many guesses at the rule and then selected the average. And I think we see here the introduction of a higher level of organization. This final selection process creates a meta rule, a rule of rules. And this meta rule acts as a dynamic constraint. It literally selects away all the noisy, random, incorrect predictions from the individual trees, and it channels the system's final output so that it conforms to a better approximation of the pattern. And I think this is precisely what Terry Deacon identifies as formal causality, a higher level organization that works by imposing constraints on its constituent parts. And I believe then that since the trained model has the capacity to shape new sign vehicles into forms that correctly correspond to the patterns in the inputs it is given, and that its capacity to shape these sign vehicles was not explicitly specified by its creators, we can conclude that it operates not only on the basis of efficient causality, but also on the basis of formal causality. I also propose that this formal causality is itself a dynamic feature whose very existence is contingent upon the complexity and hierarchical depth of the system's organization. But I can imagine the objection from a hard-nosed computer scientist, and maybe some of you are thinking this as well. They would say, hold on, there's no formal causality here. You're just adding philosophical jargon to what is a perfectly mathematically explainable process. Every single action in that computer can be decomposed into a sequence of simple dyadic interactions. There's nothing there but electrons pushing other electrons. And guess what? They will be partially right. The higher level I'm describing, of course, includes those electrons. But it's also more than that. If this system operated only based on efficient causality, we would not find that aggregating many individual trees would produce the ability to generalize. If it was nothing but dyadic interactions, there would be no reason to expect that mechanically adding the result of hundreds of weakly predictive trees would produce a strong tendency to generalize. So there's more here than electrons pushing other electrons. We also have relations that organize how those electrons push each other. And in automated learning systems, such relations appear during the course of the training phase. We could say that such systems have two phases. First, they reverse engineer the formal causes that gave rise to the formal relations latently present in the images stored in memory. And once they've done this, they can approximately enact them autonomously. And I should be very clear here. I'm not saying that there's any final causality here. There's no genuine thirdness. There's no semiosis. There's no sense of normativity guiding such systems. There's no underlying metabolic pressure constraining their movements. There's no living idea connecting to the heart of reality itself. However, to say that there's only secondness is not right either. To decompose the process into its dyadic interactions is to miss the very principle that makes it work, the set of emergent formal relations that exist between the parts as an organizational constraint. And I believe Peirce was onto this when he talked about first and second degenerate thirdness, or in other words, that there are degrees of mediation. Learning systems like these can learn to mediate in a very limited way. They approximate patterns within very small collections of patterns. Outside, in reality at large, where there are patterns all the way up and all the way down, they fare very poorly. Though it's important to remember that I deliberately chose a very simple system whose organizational depth is very shallow. But I do think it provides the proof of concept for a much larger idea. And the principle is this: the emergence of degenerate thirdness depends on the hierarchical depth of the system's organization. The deeper the hierarchy, the less degenerate the thirdness. A shallow system approximates a pattern. A deep system approximates patterns of patterns. A massively deep system approximates patterns of patterns of patterns. And when I look at the kinds of learning systems being rolled out today, I think that's precisely what we are witnessing. So let's bring this all home. Why does this distinction between efficient and formal cause matter? It matters because we are integrating these artifacts into our own cognition. And this has novel consequences. Let's return to our team of ecologists studying whale vocalizations. In the past, they might have spent their career analyzing a few hundred hours of audio. Now, by integrating a tool like random forest into their cognitive assemblage, their assemblage becomes vastly more powerful. They can process decades of hydrophone data covering entire oceans, analyzing patterns in acoustic spaces with thousands of dimensions. And of course, the patterns the algorithm finds are in themselves meaningless. Only the teleological framing of the ecologist would imbue them with significance, whether they indicate an increase in stress due to noise pollution, reveal a novel nuance in a mating ritual. But here's the crucial point, in the heart of my conclusion. Note that the logic of constellational unfoldment I just outlined only goes in one direction. The algorithm produces the patterns, and the ecologists decide what they mean. But constellational unfoldment is not a one-way street. Because these systems are able to approximate formal causes in vast data structures, they are effectively able to vastly proliferate the availability of patterns ready to be imbued with significance and meaning. So while it's true that learning systems blindly detect patterns without having any kind of goal, they are able to greatly expand the space of possible goals that ecologists can pursue. And because of this capacity to operate on the basis of formal causality, the teleodynamic space that ecologists operate within becomes reconfigured. So what we're witnessing here is a technological scaffolding of Deakin's nested hierarchy. The efficient cause of the electrons, the raw physics, the homeodynamics, is organized by the emergent formal cause of the model, its morphodynamics, and this in turn provides a new and vastly expanded space of possibility for the teleodynamics of the human scientists. Or in Peircean terms, the system's degenerate thirdness scaffolds and makes possible new kinds of genuine thirdness. Going forward, we should expect that at some point, the accumulated weight of such meaningless patterns will reach a threshold whereby a causal pressure is exerted on human cognition. It is likely that these systems will enable new forms of environmental cognition in which ecologists begin to reason within more multi-layered, temporally complex possibility spaces, spaces that are opened up by the vast web of formal relations that machine learning can uncover. And I would suggest that it is biosemiotics, a discipline uniquely equipped to trace the intricate pathways between efficient, formal, and final causality that possesses the appropriate conceptual grammar required to navigate and ultimately give meaning to this new condition. And with that, I thank you for listening. Sure, there will be questions.
There's a stat, let's say, within we could see technological tools as a part, the complexity, sorry, complexity. Also, in a sense, Andy Clark's extended set, this is a part of us and the way we would make sense of the world, but on a level of complexity that it's scaffolded on a higher level. Would you say that? Like a part of
I love your question. Can you phrase it again so I understand it more clearly?
this? Would you see technological as part of biological? So
What do you mean by the biological human?
it's still
For sure, yeah.
so they are not in that something like not sure. This is what so to distinction.
I'm not sure I would go there. I've been trying to understand how these technologies create new kinds of understanding in environmental science. And this way of understanding the relationship between formal cause and final cause, I think, works on the level of cognition. For certain, there is entanglement between our biology and technology. I'm not really sure that this framework is able to clearly speak to that.
Before giving the floor to Heinrich for his question, can I hazard a reinterpretation of your question? So all of this decision making, right, is not somehow autonomous, right? It was created by humans as a sort of extended cognition for us, right? So I think there was a recursivity in that question because we tend to reify, to use an old school word, these are artifacts, especially ones that give us life, like pareidolia processes. Like, oh my gosh, it's giving us new patterns, which are like the patterns that we make sort of in an analog version, but they're doing it digitally. And they're doing it digitally in not just a sort of a dumb coding and decoding, but they're using all these frameworks, which probably all organisms use, but they're able to do it in a different way, like a say a way where you can see the work.
Yes. Yes. And I mean, I presented an example where it's like it's kind of like the operators set the start button and then the thing produces the pattern. In reality, it's way more recursive. I mean, if you just look at someone who's doing this, I mean, it's a total back and forth. And I think it's a way more complex framework required to kind of get at the recursive entanglements that's happening there.
In your example, you had a training set of well-defined values. This is digit 8, so on. And I sort of see that as a source of the 2.5-ness that emerges. Do you think that would emerge if you unsupervised training, like self-organizing that?
I don't know, but I mean, the great thing about this framework is that you can test it, and it would be really cool to get people who knew machine learning to kind of come on board, and then you can run tests to see. My hunch would be that you do, but it depends on the training data and the training time. And I mean, there are lots of examples where unsupervised learning gives you great results. And it does converge on this ability to generalize.
So, quick question from Tim, and then we need to move on.
Yeah, I really enjoyed the presentation, and a while since I did anything like any systems, but I'm probably out of date, so I'm taking the opportunity here to ask, do think, are these decision-making systems, is there any abduction going on in them? The reason I ask that is because the first meeting I Paul Virginia and Francisco Varela, they wrote a paper toward the practical autonomous system, and this is the thing I always refer back to. They said the main challenge of this decision-making system in AI was to produce a abductive machine. And whenever I've asked the question, well, someone says yes, and I ask if yes, they don't quite believe it, and then it's, yeah. So I just wondered what your
Again, I think it depends on the system. And I mean, one answer is no. Another possible answer is like, what's between induction and abduction? Like, if you massively scale induction, is it still just induction all the way? If you get this massive parallelism, which is kind of what these systems do. I mean, they're not simultaneous, but they're not sequential. They're just massively parallel. So it's really they're neither sequential or simultaneous. And I'm guessing the relation between induction and abduction is something like that. It's something in between. Thank you.